So let us start with the today's class, that is the electrochemistry, which is one of the very important chapter again. This chapter usually gives the numericals in the question paper, and these numericals are actually easy, and the students are gaining good scores, okay, in this numericals. But many times there are some small mistakes done by the students because they lack some uh, little bit deep knowledge of the chapter or the topic or the concept, lacking in the concept, okay, which needs to be clear first. So electrochemistry is a branch of a chemistry which deals with electricity, generation of electricity, okay, using chemicals, okay, generating of electricity using chemicals or vice versa, vice versa, okay. So it deals with the interconversion of chemicals and electrical energy. It involves redox reactions. So before you start this chapter, uh, concept of redox, reduction and oxidation must be understood, okay, by all of you. Redox reactions are actually the transfer of electron. We'll just revise what are oxidation. Oxidation means loss of electron. Suppose if I have copper and copper loses electron, it becomes U 2 plus 2 electron. So this process, because the copper is losing here electron, loss of electron, we call it oxidation for copper here. The same way, reduction is gain of electron. Let us say the same like the Cu plus 2 ions I have, it gains 2 electron, then it will turn into a solid metal copper. Now this is the reduction because here there is a gain of electron is taking. Reducing agent. The species which donates the electron and get oxidized is called reducing agent. Similarly, oxidizing agent is the species which accepts electron and get reduced. Now, there are direct redox reactions. So, for example, if I have a container and in the container I have kept copper sulfate solution, which is going to give me copper ions and sulfate ions. And in that, suppose if I dip okay, uh, zinc metal, which is a solid state. Now, what will happen here? The zinc being more reactive, okay, will displaces the copper. It will displaces the copper. So there is a direct redox reaction taking in a single container. Okay, so there is a direct reaction taking place in a single container. We call it a direct redox reaction. So this is a direct redox reaction. In the same container, you will find that okay, the zinc is displacing the copper ion. So what happens with the copper is copper ion gets electrons from zinc. Now these two electrons are obtained from zinc. Zinc loses two electrons. That's converted into Zn plus 2 and 2 electrons. Now this 2 electron goes to the copper. The copper is formed. Now this brown coating you can see on the electrode is copper. So both redox reactions are taking place in the same container. We call it a direct redox reaction. In direct redox reactions, we will be having two separate containers. Now see here in the diagram, we are having two separate containers. Okay. In one container, there is an oxidation process going on, and in another process, there is a reduction is going on. Okay. Now, usually for the ease of understanding the electrolytic process, in your left hand side, always try to have the oxidation. Always try to have the oxidation process. On the right hand side of your diagram, try to have the reduction. You can remember like R goes with R. Right hand side, reduction. Okay. Left hand side, oxidation. So the metal here is going to get oxidized, and here the metal is going to reduce. Okay, the Cu+2 ions in the electrolyte will gain electron. Okay, and here zinc will give away electron. Now, why the electrons moves from zinc to copper? That is a question. Okay, why or what is the need? Okay, that zinc has to give its 2 electrons to copper so that copper ion gets converted into copper metal. This is all. Why there is a need? Okay, so this can be understood by knowing the concept of reduction potential or potential. Okay, before that, let us understand what these cells are actually. The cells are known as a voltaic cell. Voltaic cell. Why do we call it voltaic cell? Because if you look at this, there is a generation of electricity. There is a flow of electron. Flow of electron means electric current, and whenever there is a current, we always have a electric potential V. Potential difference is created between these two terminals. Which are these two terminals? These are the two terminals you can see of the battery. Okay. In This is a simple setup of electrochemical cell. We will learn this as a class. Right? Okay. Now let us understand what is a salt bridge. Now in the diagram here, if you see, the electric current is flowing. The electrons are moving from zinc to copper. Okay, so the current direction of current will be opposite to that of the flow of electrons. Okay, now current okay, that's a B point. Uh, this is the point C, and this is point D. The current is flowing through A to B, B to C, and C to D. What about D to A? Now the circuit is incomplete. How the circuit will get completed here in the liquid state or in the aqueous state, which we call as the electrolyte. So here ions flows. Here ions flow. How do these ions flow then? Now here ions flows through this semi-permeable membrane. This is a semi-permeable membrane, which we call as a SPM, semi-permeable membrane. In most of the reference book, in short, it is written as a SPM. So the selective ions are moved across this semi-permeable membrane, and hence we get a complete set. What if I do not have? Okay, this is a SPM, semi-permeable membrane. What if we do not have the semi-permeable membrane, and instead of the big large container, we are having two separate containers? Say for example, beaker 1 and beaker 2. Then how will they get connected? So in that case, we have to connect a salt bridge. A very famous and very oftenly repeated asked question in the board exam is, what is salt bridge? Okay, and what is its function? So salt bridge actually connects the two different containers. That is an oxidation half. Remember, we have decided that left hand side is going to be my oxidation process. So we can call it oxidation half cell. Okay, and this is the reduction half of the cell. Okay, so reduction half of the cell. So What salt bridge does? Salt bridge connects these two cells, half cells, reduction half and oxidation half. Okay. And what is its purpose? It completes the circuit. It completes the circuit, number one. Okay. And maintains the electrical neutrality. Now, what is this electrical neutrality? Now, remember in oxidation half cell, zinc is continuously losing electrons. So, what will happen? Zinc ions are formed. Zn plus 2 is formed. Every time when the zinc atom loses 2 electrons, Zn plus 2 is formed. Okay. So, slowly and gradually, what will happen? That in what we find in the oxidation half, the concentration of zinc plus ion increases slowly and gradually. So the solution become highly positive. The solution will become highly positive. So this is now positively charged solution. Now this positive charge will pull these electrons back. The electrons which are going to Cu plus 2 ion. Here Cu plus 2 ion is pulling the electron, is pulling these electrons which are coming from the zinc. So this positive charge will not allow these electrons to move towards the copper. And slowly and gradually what will happen? The cell will not work. That means the electric current will not flow. Why? Because the excess of zinc will not allow electron to go out from this oxidation half cell. So to neutralize this sudden, we have to add some negative anion, negative anion. So that positive cation Zn plus 2 and anion together becomes neutral. So in salt bridge, this is a salt bridge which is having an agar-agar medium, and in that we have a KCl. So what happens is Cl minus ions from KCl goes into this beaker, okay, beaker 1 filled with zinc, and neutralizes zinc plus 2 by making ZnCl2. So the positive charge will now will decrease and hence the flow of current continues. Same way, if I keeps on adding electrons to copper plus 2, what will happen? Copper atoms will deposit on the copper metal strip. So what is the negative ion? We have taken copper sulfate. Remember, copper sulfate. So copper ions are now going into the electrode in the form of a Cu, copper. So slowly and gradually the concentration of Cu plus 2 will decrease and sulfate ions will keep on increasing. Again, what will happen? More in the reduction half and this negative charge, okay, hence it increases negative charge in the reduction half. And now this negative charge, too many sulfate ions will repel this coming electrons. The electrons are coming from Zn, remember this. So this electron will find repulsion from by the electrolyte and this electrons will not. So again, I have to neutralize this sulfate ion. So what happens? The KCl, which is used as a salt bridge, the potassium ion will come here and neutralizes my sulfate by making K2SO4. Okay. So the sulfate ions will get neutralized. So salt bridge has function one to complete circuit. Okay. And second important task is to maintain the electrical electrical neutrality. Neutrality of the solution. Fine. So now, what happens now? Cell potential. What is the meaning of cell potential? In simple general words, when we have a system of two water tanks connected with each other. Okay, suppose this is a tank A and there is a tank B. The water in the tank A is filled. There is a tap in between, so there is no flow of water, and there is a appreciable difference in the height of the water levels. Once the tap is open, what will happen? The water from the higher potential will start moving into the tank which is having a lower potential. So slowly the water will rise here and water will go down here. Till what point this water will continue? Once the level of water is same in both the containers, the water will continue flowing from higher potential, higher potential until what point? Till the change in this potential delta V, change in the potential becomes zero. Okay. So if you maintain the potential difference, the water will continuously flow. Same thing happens if you assume that instead of water, I have lots many electrons here and less electrons in the B tank. So if you open the tap, the electrons will start moving from one tank to another. Till what point? Till the potential difference becomes zero. Now, how to create this potential difference? How to create the potential difference? How to create a potential difference? And what is this potential difference is actually? Now, to understand that, if you understand the meaning of reduction potential or potential difference, or even potential, the chapter is going to be very easy for us. Okay. So now, what is the actual meaning of cell potential? Suppose if I have a container and I have taken the solution copper sulfate, aqueous copper sulfate. Copper sulfate is going to give me copper plus 2 ions and sulfate ions in the solution. In this solution, I will be having copper plus 2 ions, okay, and sulfate ion. Sulfate ion, right now I'm not writing, I'm not writing, okay. And let me add a metal which is made up of copper. This is a copper metal with electrode. Let me call it electrode. Electrode, copper sulfate is electrolyte. Electrolyte. Now, what will happen between the solid copper electrode and aqueous copper ions? This is copper ions which is in the aqueous state, and the cations, positive. Now, positive ions has a potential or capability to attract electron. Remember, metals are one which gives electron easily. They gives n electron. N means as per their valency. Some metal gives 1 electron, some gives 2, some metals give 3 electrons. So let me have that n as a number of electrons. In our case, copper can give its 2 electron. Because it is a metal, it has a tendency to give away 2 electrons. Not two, this 2 electron will go to home. Copper ions in the solution will attract those 2 electrons. So they will get electron and they will get deposited on the metal surface, because the surface they are getting the electron. So you will say that the copper ions are going out of the electrode, okay, and from the solution copper ions are going back into the electrode. So what is actually happening here? So you can say that there is a equilibrium set. Say for example, if 100 particles of copper ions comes out from the electrode, at the same time 100 ions from the solution will go back into the electrode. So there is an equilibrium. Now why this is happening? Because we can see that copper ions requires electron. Suppose if I have a zinc instead of copper, then what will happen? then the solution will become zinc sulfate. The solution will become zinc sulfate. Suppose if I have a zinc electrode is dipped in a solution of a zinc sulfate. This will give me zinc ions, and this is zinc metal. So same thing will happen. Zinc ions will come out from the electrode, and zinc ions from the electrolyte will go into electrode. So there is a tendency. If you see why this is happening, because here the cation zinc plus 2. In our previous case, copper plus 2. Both of them were having one tendency. And what is the tendency? The tendency is to gain electrons. Zinc plus 2 ions wants to gain 2 electrons and wants to get converted to zinc. Same way, copper plus 2 ions also wants to gain 2 electrons and want to get converted into copper metal. So this is a tendency of a cation to gain electron. Gain of electron is nothing but reduction. Gain of electron is called reduction. So you can say that the cations are having tendency to show which property? Reduction property. Okay. Now the question comes, both the reactions look similar. Absorption or gaining of 2 electrons by the cation here zinc and gaining of 2 electron here. Sorry, there is a correction here. Plus 2 electron and copper. Okay. So both the processes are same, gaining of 2 electron. The question comes, do zinc gains 2 electron with the same ease that the copper ions gain 2 electron? Answer is no. They have a difference. Copper plus 2 ions gain 2 electron with more ease because it has a higher tendency to absorb electron. Copper plus 2, let me draw copper also side by side so we can compare. So this is copper plus 2 and this is a copper metal. So copper plus 2 has a higher tendency to gain electron. It will gain electron. Okay. And zinc plus 2 has a tendency, but it has a lower tendency to gain electron. So now let us replace this word tendency with potential because both are same. So instead of saying tendency of gaining electron, let me call now this as a reduction potential. Okay. Electron gaining tendency, okay, which is a now layman term. I'm using now it as reduction potential. Reduction potential. So which is having higher reduction potential? So copper plus 2 has higher reduction potential value than Zn plus 2. So now what will happen here? If I connect zinc with copper, because the copper plus 2 ions have a higher tendency to gain electron, it will gain electron from copper. So copper will attract electron from zinc, and zinc has to give the electron to the copper because here copper plus 2 ion is stronger. It is having a higher reduction potential value. It has a higher tendency to gain electron. Zinc is here to give electron. How many electrons? 2 electrons. Zinc will give 2 electrons, definitely. But to which cation it will give? Will it give to zinc or will it give to copper? Because they are connected now with the external circuit. Okay, so electrons can go directly to the zinc or electrons can go to the copper ions via this outer circuit, external circuit. So what will happen here? Because the tendency, reduction potential of copper plus is higher, it will start gaining electrons. So instead of giving electron zinc to the zinc plus 2, it will give now electrons to copper, which further gives electron to the copper plus 2 ions. Now we have a flow of electron. flow of electron. Okay. Now, this flow of electron is nothing but the electric current, and we know that electric current is very important. Electrical energy can be converted to many other forms of energy. So ultimately, we have created the current. Okay. Now, why this happened? Because reduction potential, again, reduction potential of copper is more than zinc. How much is the more? So what we have to do? I have to find out difference. How much means the higher potential minus lower potential. That means I have to talk about the difference in this reduction potential. And this difference is nothing but we call it as a potential difference. Okay, we call it potential difference. Potential difference. And how to calculate potential difference? Okay, so the potential is given by E. Standard condition means keeping temperature 298 pressure at 1 atmospheric pressure. Okay, the reduction of cathode minus reduction potential of anode. Sorry. Anode. Okay. Now, this is change in reduction potential. Now, if you are talking about reduction potential, why we are not talking in terms of the oxidation potential? If some element has, or a metal salt has a tendency of gaining electron, why we are not talking in terms of loss of electron? Because for the electrode zinc, you can see this as a loss of electron. Why we are not talking in terms of oxidation potential? You can solve similar case with respect to oxidation potential also. But IUPAC says it will be preferred. It will be preferred if we talk in reduction potential values. Reduction potential values instead of oxidation potential values. And why does it say that the reduction potential value should be taken? Because oxidation potential value, if we are taking, say for example, okay, two chemists are talking together, okay, for cell potential, and one is talking in terms of reduction potential, another is talking in terms of a oxidation potential. Then there will be confusion because one is talking in terms of loss of electron, another is talking in terms of gain of electron. So these two concepts together cannot be studied. So both of them has to either talk in terms of loss of electron, or both of them has to talk gain of in context of gain of electrons. IUPAC says that internationally, globally, let us talk in terms of a reduction potential. So reduction potential values, okay, are called standard potential value, are now as referred as a standard potential value. Potential value. The standard potential values are nothing but the reduction potential values of your cation. Say for example, we studied copper plus 2 ion has a higher tendency to gain electron than zinc. So I am reframing the same statement as reduction potential value of copper plus 2 to get converted into copper is higher than the standard reduction potential of zinc ions to zinc. This is how we denote. And the difference between these two is nothing but delta V. Delta V, usually we call it potential difference. In electrochemistry, we call it E, E cell, because we are talking about now cell, E cell. Okay, E not cell. Okay. Now, how do we know the difference? For this difference, we should know the values. We should know the values, that what is the value of copper plus 2 to copper ion. So there is some numeric value. There is some numeric value for this, and there is a numeric value for this also. Okay. And how do we get? We get these values by comparing. Okay, by standard hydrogen cell, SHE. Before going that, before studying that, let us have this simple points. What is cell potential? Cell potential is electromotive force, also known as EMF. The difference between EMF and cell potential is EMF is a potential difference across the terminal of the cell when no current is derived from it. Okay. Say for example, a dry cell is there with you. There is a dry cell. Okay. When it is not used, that means when its terminals are not connected, it shows 1.5 volt. But once the terminals are connected, there is a flow of electron. There is a flow of electron, or you can say the flow of currents takes place. Flow of current takes place. Now, when there is a flow of current, what will happen? Some potential will get used up in overcoming the resistance of the circuit. So I will actually not, suppose if I have a potential voltmeter here, that how much potential is across these two terminal, positive and negative, then it will not show me 1.5. Why? Because some potential is now used up in moving the needle of your galvanometer or potentiometer, or overcoming the resistance of the wire external circuit. Okay, so that is the cell potential. We call it cell potential. EMF is when there is no current. It is a theoretical value. It is theoretical. Once you calculate it through some device, definitely in moving that device, some current is used. So that is cell potential. Okay. So, uh, electric potential difference between two electrodes are, or the half cells, depends on the specific half reaction concentration and temperature. Now, how this cell potential depends? It depends on the half reaction. It depends on the concentration of your ions, cations, that is Cu plus 2 and zinc plus 2. It depends on the temperature also. So there are three factors which affects the cell potential. Number one, which cation you are taking. Okay, that is, you are taking copper, zinc combination, or you are taking iron and say magnesium combination. Okay, so which type of cation combinations you are taking. Okay, so specific half reaction depends on the concentration. What is the concentration of your ions which you are taking, solutions concentration, and the temperature. Under standard state condition, solute, usually it is 1 molar, atmospheric pressure is taken 1 atm. Okay, and we calculate the standard cell, E naught of the cell. Remember, 1 volt is equal to 1 joules per coulomb. Okay. So now this is E cell. What is E cell? It is the reduction potential at cathode. Cathode is on the right hand side of your cell, RHS value. RHS value. Anode is on the left hand side. Left hand side. We have studied the reduction potential. Right hand side, we will take Right hand side of the cell, we talk about reduction, reduction, and left hand side, we talk about oxidation. Okay, oxidation. This is usual diagram. You can draw other way around as well. There is not an a, this is not a hard and fast rule, but mostly you will find in the reference books or standard books, you will find the right hand side, usually they are indicating the cathode or the reduction process or the reduction half cell. Okay, so in different books you may find ERHS minus ELHS, or you can write E cathode minus E anode, because the electrode which is dipped on the reduction half cell is known as a cathode, and the electrode used in the oxidation half is known as an anode. Okay, or sometimes it is also denoted by E redox minus E oxidation. Okay, these all formulas are the same, the meanings are same, the way of writing them are different. Okay, if it is used in the standard condition, we put not sign here. This not sign indicates that potential difference are taken at a standard state. Okay? And these values, now see, E cell can be measured, but absolute E cathode and absolute E anode cannot be calculated. Suppose somebody says that what is the value of E oxidation? We cannot calculate directly. Okay, we cannot calculate it directly. So they are absolute values. We cannot calculate. We can find the difference between two cell potential. Okay, so potentiometer or galvanometer, which we are using to find the difference in two potentials, it only gives us the difference. So difference, it is possible, like say one potential is at 100, another potential is at say 110. So what is the difference now? The difference between these two is, let us say, 10. Similarly, let's say one potential is at 0, another potential is at 0. What is the difference here now? Let's say 10. Suppose one potential is 50, another potential is at 60. The difference is 10. So this difference is more important, which actually responsible for the current to flow. Okay, irrespective whether the potentials are at 100 or 110 or 0 or 10, okay, or 50 or 60. What we need is a difference between these two potentials. Okay, so what is this line? Absolute potential. We cannot calculate this 100 and 110 directly. Okay, so if I have to calculate this 100, I need another cell, okay, which has to be compared with. So it is a, you can say, the relative term. Okay, these are the relative concepts. And for that, we are using hydrogen cells. That is a SHE, standard hydrogen electrode, which has a potential is equal to 0 volt. Now, how does it work? Hydrogen SHE, the preparation or the setup of hydrogen cell is usually asked. So there is a glass hollow tube. There is a electrode which is made up of platinum. This is the platinum plate, further coated with the platinum, finely powdered. Powdered platinum powder is coated on the platinum plate to increase the surface area. This is the acid which has a concentration of 1 molar. 1 capital M, you can take HCl or H plus ions, and hydrogen gas at 1 atm is passed through this setup. Okay, and the potential of this cell is equal to 0 volt. It gives us the potential at 0. Now suppose I want to calculate the potential of the copper connecting with the hydrogen. I connected with the hydrogen. The potential of hydrogen is 0 volt. Current potential of copper, I don't know. Let us say that we have X. I don't know standard copper plus 2 to copper. I don't know this. Okay. So what I can do is I will set up the similar device. This is a voltmeter and this will give me some value. This is plus 0.34. Okay, how do I connect? How do I got this? So E cell, this is nothing but the E cell. E cell of this entire setup is equal to E cathode, that is a potential at right hand side, minus potential on the anode. Anode. So cathode has a potential of 0. Sorry, value of my copper, that is X. This I will get. Now, what value do I am getting? I am getting here 0.34 volt. This value give me 0.34 volt. So if I remove this 0, what value? Actually, this value should here show me a negative value. Okay, this will come as a negative value. So if I do like this, the minus minus will get cancelled, or a higher potential minus lower potential if you do, okay, then the value will become positive. So this 0.34 potential V belongs to what now? Copper, because what is the contribution of hydrogen? 0. There is no contribution of here hydrogen. So pure difference between these two cells, okay, reduction and oxidation half cells are what? 3.4, and that is coming purely because of the copper. Similarly, suppose if I replace this with zinc, okay, and potential what I get for zinc, we get minus 0.76 potential. Okay, so now suppose if we connect, okay, like this, we have the different reduction potential values. Okay, look at this, what reduction potential values. Fluorine, this is Au plus 3, like that. This is the highest value right now in the table, and this is lowest potential value. Lowest potential value, which are shown in the negative. Hydrogen in between you will find as a 0. Okay. So suppose if I have a cell made up of copper plus 2, and where is our zinc? Zinc. How do I get the E cell? Suppose if we connect copper and zinc, okay, then what will be the value? So our formula is E cell, E cell E naught cell is equal to E cathode minus E anode. Okay, so which out of copper and zinc will behave as a cathode? Which will behave as a cathode? Now look at these two values. This is positive 0.34 and this is negative. 0.34 is bigger value than minus 0.76. So higher potential is always the right hand side, that is a reduction half cell, which is always a reduction half cell. Okay, and fine. So here you can see that the right hand side value is 0.34. Copper will behave as a cathode, E cathode, and zinc will behave as a E not as anode. So the correct E cell difference now will be 0.34 minus 0.7. always keep the reduction potential, higher potential values at cathode and the lower potential values at anode. So if you see the difference, is your answer. Okay, you can see this in a coming question. Fine. So E cathode is always greater than E anode. And if this thing happens, the cell is spontaneous. That means the cell is useful for us. The cell will work for us. If E cathode is smaller than E anode, okay, then the cell will not work for us. It is a useless cell for us, okay, or there's a need of recharging it. You have to recharge it. What we do with our mobile phones, we recharge them. Why? Because the cathode and anode become the similar. They become same value. So difference becomes zero and the mobile doesn't work. So you have to recharge it. That means the cathode potential has to be increased once again so that there is a flow of current from cathode to uh, you can solve one small numerical here. Okay, what will happen if we have a silver nitrate and copper electrode? Okay, dipped in zero point 0.1 molar silver nitrate, Ag electrode in silver nitrate, copper is copper electrode. So first we have to find the E cell, which is asked here. What is E cell? The E cell here. So the formula is E cathode minus E at anode. Reduction potential value at cathode minus reduction potential value at anode. How do we know that which will come at cathode? So let us see the values. This is a table. This is silver, 0.8. Remember, this is plus positive value. Okay, and uh, another is copper, that is 0.34. Out of these two, which is bigger value? Definitely 0.8 is bigger than 0.34. So this is now become cathode. Okay, this will become cathode. This will become anode. So if you put the values there, 0.8 minus 0.34. Okay, and the answer which we will get is 0.8 minus 0.34, which give us 0.46 So if I have to connect this combination, the potential difference will be 0.46 volt. So you can do this as an example: nickel nitrate and ferrous nitrate. Okay, so we have to know now the potential of nickel, that is 0.23 negative value, and ferrous Fe plus 2. So which is bigger? Definitely here now 0.3 negative value is bigger than 0.44, which is negative. This value is bigger. So what will be the E cell of the cell? E cell will be higher value. This will become now cathode. This will become now anode. Okay. E cathode, E cathode minus E anode, that is minus 0. This will be with the value minus 0.23 minus value 0.44 will be 0.21. 0.21. Okay, 0.21 positive value. Here, the cell will work because we are getting a positive E naught value. Okay, potential value. So guys, today just we completed how we can find the cell potential and E cell of any cell. Okay. Now, if we change the concentration, if I change the concentration, say in this question we have 1 molar, okay, 1 molar. Instead of this, suppose if I take 0.01 molar, will it affect the E naught cell? Answer is yes. How does it change? For that, we have to learn the Nernst equation. Nernst equation. Okay, so Nernst equation is the equation, just a modified form of this E naught cell, E naught cell, okay, uh, E cell minus some value. Here you will find log of right hand side, left upon left hand side, you can say, okay, to calculate the E naught cell. Why? Because we are now changing the concentration. If it is 1 molar, you can simply go with this small thing, that is E cathode minus E anode. E cell is equal to E cathode minus E anode. But one correction in this formula. This is not. This is E naught cell. We just learned how to calculate E naught cell today. Okay. But if the concentration changes, if the temperature changes, okay, then the E naught cell will not be your E cell. There will be some change in the potential difference. And that is given by the Nernst. So if you do the Nernst equation, guys, it will be easy for you to understand that how the potential of the cell is obtained. Once you complete the Nernst equation, then a very simple topic of cells, dry cell, lead cell, fuel cell, these topics are there in the syllabus which you have to learn by the reaction at anode and cathode, their preparations, uh, how do they work, primary batteries and secondary batteries. So these topics are usually exam. So once you do the Nernst equation, few examples and the cell topic, that is the battery is done, the chapter is done from your side. Okay, guys. So in the next class, if you doubt, anybody has a doubt? No. So in the next class, we'll meet with another chapter. In the meantime, you can go with the Nernst equation and types of batteries, primary and secondary batteries.